Yeah, Amudha ma'am.
Yes, sir.
Shall we start, ma'am?
Yes, sir.
Okay. Okay. Good afternoon to one and all. On behalf of the management and principal of St.Joseph Institute of Technology, on behalf of the Department of EEE, I welcome you all for the fourth day, third session of AICT sponsored online faculty development program on aspects and machine learning applications in smart grid. It's my privilege to deliver the citation of an eminent personality, Amudha ma'am. Okay. She has well experienced design engineer with a demonstrated history of working in the design of power systems, skilled in power engineering, electrical engineering, generators, power distribution and transformers. Strong professional with a master degree focused in power system from College of Engineering, Gindi. She has published his paper related with ABC algorithm based voltage stability enhancement strategy for distributed distribution system. His top skills is project engineering, power systems, electrical engineering. She was working for past 4 years in power projects. Ma'am,
Yes, sir.
shall you take the session, ma'am, now?
Yeah, sure, sir.
Yeah, okay, okay, thank you.
Very good afternoon to everyone. I will share my screen now. Sorry, is my PPT visible?
Yeah.
Hope my PPT is visible.
No, ma'am, your PPT is not visible, ma'am.
It's okay. Is it visible now?
Yeah, ma'am, now visible, ma'am.
Thank you, thank you.
Okay.
Very good afternoon once again. So the topic of the session is renewable integration, role of renewable integration and power quality issues. Before going to the role of let's discuss what is power quality and what are all the power quality issues, because we'll be discussing the limits of harmonics and power quality limits in the grid integration, that is the grid code requirements. So without knowing these power quality issues, if you move on to the renewable integration, it will be meaningless. So let me give some introduction about this power quality issues, and then let's move on to renewable integration. So the agenda of this session is introduction to power quality, next the need for power quality, next what is harmonics and what are all its effects, next optimized advanced solutions, next case study. Okay, so coming to the introduction of power quality. So what is power quality? Power quality is nothing but maintaining a sinusoidal waveform of bus voltages at its rated voltage and rated frequency. That is, we have to maintain three parameters of bus voltages. That is the rated voltage. So the magnitude of the voltage has to be maintained, and then rated frequency. The frequency should be maintained, and then finally the wave shape. So the wave shapes should be sinusoidal. So if these three parameters are maintained for a bus voltage, then we can say that the power quality is maintained well. So we have a very good power quality. But if any of these parameter is not maintained, or if it is deviating, or if it is a fluctuating one, means then we can say that the power quality is not ensured, and we may face a poor power quality. Okay, so power quality is maintaining a sinusoidal waveform of bus voltages at its rated voltage and rated frequency. Okay, so what is the need for this power quality? Once if we are not maintaining the quality of power, what happens? What are all the effects of poor power quality? So it may overheat your equipment. If it is a transformer or a motor, whatever the thing, the equipment, your equipment will get overheated, and there may be huge system losses and line losses will be there. If it is a transmission line, losses will be more. If it is a transformer, motor, whatever it is, the losses will be very high. So this system losses will give you huge economical losses. Sometimes you may need to pay penalties to the utilities. Okay, and huge losses will also cause damage to equipment. If this equipment is very sensitive, it may cause damage to the sensitive equipments. Also, you need to pay penalties to the utilities. Sometimes many of the industries will be paying penalties if you are not maintaining the power factor, or if you are not maintaining the harmonics within the limits, means we have to pay penalties to the utilities. So this is the effects of poor power quality. So we have to maintain the power quality. Okay, once if the power quality is not maintained, it will lead to all these effects. Okay, so So some typical effects we can see that we can see flickering and blinking lights. We could have seen in our houses. So all these are because of power quality issues. That is, if, the power quality is not maintained. Sometimes there may be noise from transformers, and in the distribution equipment, sometimes it may be running hot, and circuit board failure will be there in some PLCs, and breaker trip and shutdown may be there in some drives. Breaker may trip sometimes, efficiency will be less, transients will be there. Transient is nothing but a sudden change, and sometimes a motor may fail, sometimes the communication will be poor, power factor may be poor, and you have to pay a very high utility bill. So all these are the adverse effects of poor power quality. So once again I repeat, we have to maintain good power quality. If the power quality is not maintained, we have to face all these types of issues. It depends on what is the equipment we are using. So we have to face all these effects. That is why we have to maintain good power quality at our end. So what causes this power quality to be poor? That is, what affects the quality of power. So we can say that either it may be a natural cause, either it may be due to a lightning strikes or falling of trees, all those things are natural cause. But sometimes it may be due to the operation of a transmission line. Sometimes it may be due to the use of non-linear load or power electronic loads. So all these are the causes of poor power quality. So sometimes in the operation of a transmission line, if you energize a transformer, it may cause poor power quality. If you switch on a capacitor, if you switch on large loads suddenly, or if you switch off large loads suddenly, so all these things will lead to the poor power quality. Suddenly the voltage will be unbalanced. The frequency will not be maintained. So the wave shape will not be sinusoidal. So whatever the thing that affects your rated voltage, rated frequency, and wave shape, all those things are the causes of your poor power quality. Okay, so let's see all these things in detail. So we have seen what are all the effects and causes of power quality. Now let's see what are all the power quality problems. So once if the voltage is varied, that is the voltage, so the rated voltage is not maintained, means it may lead to power quality issues. So SAG, which is nothing but increase in RMS voltage, swell, SAG is a decrease in RMS value of the voltage, swell is the increase in RMS value of the voltage, and interruption is a failure for some particular instant. So all these are because of the variation in the RMS value of the voltage. That is, the rated voltage is not maintained. So these are the power quality issues when rated voltage is not maintained. Similarly, transients or surge, both are almost similar. It is nothing but the sudden change in your voltage and frequency. That may be because of the natural cause or the artificial one, which I have seen in the previous slide. So if there is a sudden change in your voltage or frequency, then it is called a transient. It may be an impulsive transient or oscillatory transient. Both will affect the quality of power. And next thing, it may be an over voltage or under voltages. These are long duration voltage variations. If sag and swell are taken, if this is for less than a second, but if we take over voltage and under voltage, that is if the voltage variation is for a long time, is for a prolonged time means we can group under this category. It will come under long duration voltage variations, where we will be facing over voltages and under voltages. So all these are because of the rated voltage is not maintained. Coming to the other PQ problems, we have harmonics or voltage fluctuations. Voltage fluctuations is nothing but flickers, right? So we could have commonly heard the term flicker, which is nothing but voltage fluctuations. So harmonics flickers are all because of the frequency. I mean the frequency deviation. That will be the frequency will not be maintained and the wave shape will not be maintained. So the wave shape has to be maintained sinusoidal. Once if it is not maintained in the sinusoidal one, they can call it as a harmonics is there, distortion is there, and finally we will call it as a harmonics. So let's see this harmonics in detail now. But before that, these are all the power quality problems we have seen. So harmonic distortion is given detailedly in IEEE 519 2014 standard. So once if the wave shape is not maintained, it will lead to distortion. So some of the waveform distortion problems are DC offset, notching, noise, harmonics, and interharmonics. You can just see this clearly in waveform. So here you can see that the wave shape is not maintained sinusoidal, so which cause the power quality problems. So it may be either a harmonic or it may be a noise or it may be a notch. Here you can see this is a notch and this is not sinusoidal. So all these power quality problems will distort the wave shape of your waveform. Okay. Now let's see this harmonics in detail, because the grid code requirements which we are going to see in the next session will completely deal with this harmonics. So let's see this harmonics alone in detail. Harmonics is one of the major power quality issue among all the other one. So what is harmonics? Harmonics are nothing but if or currents, either if it is a voltage waveform or current waveform, if it has frequencies, that is multiple frequencies of the fundamental one, then we can call it as a harmonics. Say for example, if we have a 50 hertz system, there are 150 hertz waveforms, and if the system have 250 hertz waveform, then we can call it as voltage harmonics, because it is having a multiple frequencies of the fundamental frequency. So 150 is nothing but the third multiple of 50. So 250 is the fifth multiple of 50. So all those things will together contribute to an overall waveform like this. So once if the sinusoidal waveform is not maintained, means we can call that the waveform is distorted. So this is nothing but harmonics. So once if the waveform is sinusoidal and pure, we will not be having any spectrum. That is, the distortion will be zero. But once if you are having a third harmonic or fifth harmonic, it will distort your waveform like this. So apart from your fundamental frequency, that is 50 hertz, you will have multiple frequencies like third harmonic, fifth harmonic, seventh harmonic, etc. So all those harmonics will be present in your system based on your load. So what type of nonlinear load you are using, based on that your harmonics will be present. Which order harmonics will be present, that depends on the type of load you are using. We will see what is linear load and nonlinear load. So as of now, I can say that nonlinear loads will generally create current harmonics. That is, when you use a nonlinear load, it will distort your current waveform. So the current harmonics will be produced. So it will draw non-sinusoidal current and your current harmonics will be produced. Once if the current is distorted, it will cause your voltage to distort. Okay. So the voltage will be distorted and it will cause voltage harmonics. So this harmonics injector will flow across the network and it will distort the entire system. Okay. So this is about voltage harmonics and current harmonics. I can say shortly that the current harmonics will be created first, which will finally distort the voltage. So finally, it will cause voltage harmonics. So just I can show you an example. So here if you see the green wave, just say for example it is a 50 hertz system. So take one cycle of this 50 hertz system. Okay. So if we have a third harmonic, so the third harmonic is a blue wave. If you see the blue wave, it is completing 3 cycles per second within this one cycle. Okay. So if this green is completing one cycle means this blue wave is completing 3 cycles. So which is nothing but a third harmonic wave. So similarly, if you take the yellow one, so it is completing 5 cycles within one cycle of the green one. So it is a fifth harmonic. Okay. So if it is a third harmonic, it will complete 3 cycles. So if it is a fifth harmonic, it will complete 7 cycles. So it has to complete either 3 or 5 or 7 within one cycle of the fundamental wave. Okay. So once if this fundamental third harmonic and fifth harmonic altogether is, if these 3 waveforms are combined, how we will be getting the resultant one? So this red one will be the resultant wave. You can just see how non-sinusoidal this red wave is. Okay. So in this way, your current waveform will be finally distorted. So it will not be a sinusoidal waveform, it will be a non-sinusoidal waveform. So what it says actually, the wave shape of the waveform is not maintained. So we can say that the power quality is distorted. We have a poor power quality. Okay. So this red wave is nothing but a non-sinusoidal wave, which is nothing but harmonic. Actually, we can classify this harmonics into 3 categories, that is positive sequence harmonics, negative sequence harmonics, and zero sequence harmonics. So if we take the harmonic order, the first harmonic order will stands for the fundamental. That is, if the frequency is 50 hertz, that is harmonic order 1. So it denotes a fundamental. So if the frequency is 100 hertz, the harmonic order is 2, and it denotes negative sequence 1. So if the frequency is 150 hertz, it denotes a third order and it denotes a zero sequence harmonics. Similarly, it goes on. So fourth comes under positive, fifth comes under negative, sixth under zero sequence. Similarly, seventh positive, eighth negative, ninth zero sequence. Similarly, the sequence goes on based on this harmonic order. But now let's see how these harmonic orders are classified under these particular sequence components. Okay, let's see this in detail. So just take this 3-phase waveform. Just I have taken a R phase, I have taken a B phase, and I have taken a C phase. Okay. So the 3-phase waveform is taken and it is completing, all the 3 phases are completing one cycle. Okay. So if you take the zero sequence, for zero sequence, I have shown you that third order and its multiples comes under zero sequence harmonics. So if I take the third order, say for example, if I take the third harmonic, how many cycles it have to finish? So it have to complete 3 cycles within the one cycle of fundamental. So this is 1 cycle, 2 and 3. So this is completing 3 cycles, and you can see very well that between the 3 phases there is no phase shift between them. So all the 3 phases are not colliding with each other. All the 3 waves are independent. So what it derives actually, what it replies, so there is no phase difference between these waves. There is no angle between these waves, right? So zero sequence always says that the magnitude will be same, but there will not be any phase difference between the components, right? Either if it is a positive sequence harmonics or if it is a negative sequence harmonics. So these are the zero sequence harmonics. Okay. So coming to the next one, if you take the positive sequence, here you can see the blue phase is leading the red phase and the green one. So let's take this in terms of A, B, C. So that is the phase C is leading A and B, right? Phase C is leading B and A. This is for positive sequence. So positive sequence, they have taken the seventh harmonic. So you can see it is completing 7 cycles per second. Okay. So in this, if you see the phase sequence, so the blue is leading, that is phase C is leading, phase A is lagging, and I mean phase A is lagging the phase C and phase B is lagging phase C. So this particular phase sequence is exactly opposite in this one, where for the negative sequence. Here you can see it is completing 5 cycles. So the fifth harmonic is taken for the negative sequence. And if you see the phase sequence, here The B phase is leading actually. So B phase is leading phase A and phase C. Okay, exactly the phase sequence is opposite here. So this is why we are calling the fifth harmonic as a negative sequence and seventh harmonic as a positive sequence. This you have to draw and see, then only you can just recognize. Then only you can visualize how it comes under zero sequence. How it comes under positive sequence, negative sequence, and zero sequence. Once if you draw all these things, all these harmonics, once if you draw and see, say for example, if you draw a 10th harmonic and see, for a 10th harmonic, you have to complete 10 cycles. So if you draw a 10th harmonic and see, the phase sequence will be in this order. But similarly, if you draw 11th harmonic and see, the phase sequence will be in this order. So this clearly implies that the 10th comes under positive, 11th comes under negative, and the third order multiples will come under zero sequence. So similarly, this order goes on. Okay. Okay, now let's think what is a linear and what is a non-linear load. Often I repeat that non-linear loads cause harmonics. Non-linear loads cause distortion. What are these non-linear loads? What type of loads are called non-linear loads? So linear load is nothing but a load which draws a sinusoidal current when we apply a sinusoidal voltage. So non-linear load is nothing but which draws the non-sinusoidal current when we apply a sinusoidal voltage. So always we apply a sinusoidal voltage only, but it depends on the load which draw either a sinusoidal current or non-sinusoidal current. Once if you are employing non-linear loads, that is the loads which has power electronic devices, say for example a diode or a thyristor or a CR, whatever may be. So once if you use a rectifier or inverter, a power electronic device, whenever you use, so it will draw non-sinusoidal current. Okay, so this non-sinusoidal current will distort the wave shape of the waveform. That is why it will cause harmonics. So here you can see this is for a linear load actually. So the supply voltage will be sinusoidal. The current drawn will also be sinusoidal. But if it is a non-linear load, the voltage will be sinusoidal, but the current will be non-sinusoidal. Okay. So this is nothing but a non-linear load. And these types of waves you can see in your rectifier. Okay. So only one half is there. So it is not a sinusoidal waveform. That is why I often repeat the power electronic devices, it will often cause non-linear currents. Okay. And actually this is a combination of third harmonic current, fifth harmonic current, seventh harmonic current, and ninth harmonic current. So just if all these harmonic currents are combined, how the entire wave will be. The final wave, how it will be distorted. To have a visualization on these effects, we have just presented this wave. So say for example, if in your waveform, if you have all these harmonics, how your waveform will be distorted and how your spectrum will be and how your final waveform will be. So you can have a glance on these. So regarding what type of loads will come under linear and what type of loads will come under non-linear loads. So whatever the RLC components which we see used for lighting or heaters or motors or power factor correction capacitors, all RLC elements will come under linear loads. Most of the time we will think inductance and capacitance may cause harmonics. No, that is totally wrong actually. So the RLC components that will come under linear loads only, but only the power electronic devices, either if it is a power converter or a VFD or a motor controller, cycloconverter, cranes, elevator, mills, UPS, battery chargers, inverters, and arc devices like arc furnaces, building machines. These loads will be found in the industries. Okay, so all these devices, UPS you could have seen commonly in many of the industries. So all these devices are the non-linear loads. So whenever if we employ these devices, if we employ these loads, it will draw non-sinusoidal current from your supply. Okay, so this will ultimately distort your waveform. So I have just categorized some of the non-linear loads based on the application. So say for example, if you're having a data center, you will have some power supply, that is UPS will be there, VSD will be there, that is variable speed drives, lighting loads will be there. And if it is a hospital, we may have VFD for chillers, you may have X-ray and MRI emissions. And if it is a wastewater management industry, you may have VSD again. Ozone generators will be there, UV lights will be there. And if it is an oil and gas industry, you may have drives again. And if it is an automotive industry, you may have welding equipment, conveyors, and you may have arc furnaces. And if it is a microelectronics laboratory, you may have VSDs and silicon growers. And if it is a commercial buildings, you may have again drives will be there. Usually drives will be there. And if it is a marine system, you may have again VFDs and DC drives for ship operations. So just I have categorized some of the nonlinear loads based on its application. So what are all the problems associated with this harmonics? So it all depends on the type of equipment you're using. If it is a transformer, it will be different. If it is a motor, the effect will be different. Let's see this in detail. But before that, I can say that excess overheating will be there because of this harmonics, okay, which lead to insulation breaking. Once if there is an overheating, insulation will fail. And there may be an audible noise from the motor, and it will degrade your working environment. And the efficiency of the motor will be reduced, and the life of the motor will be reduced. Okay. So I can just say this effects in detail. So if it is a capacitor, it will reduce the capacitor, noise will be there, inability to take the full load, and life will be reduced, efficiency will also be reduced. And if it is a fuse or breaker, mal-operation will be there. And if it is a transformer, the capacity will be reduced, copper losses will be high. All these are because of current harmonic distortion. And if it is a voltage harmonic distortion, noises will be there in the transformer, and the motor's life will be damaged, motor's life will be reduced, and the electronic loads will be mal-operating. Okay, all these are the effects of harmonics. So how these harmonics are measured actually? So this is measured by THD and TDD actually. So THD is nothing but the total harmonic distortion, and TDD is nothing but the total demand distortion. So THD is the square root, that is, it is a ratio of square root of the all the harmonic voltages. Okay, so the harmonic order varies from 2 to infinity. Either it may be an even harmonics in the sense the order will be 2, 4, 6 like that. Odd harmonics it will be 3, 6, 3, 5, 7 like that. So generally the harmonic order starts from 2 to infinity. You have to consider the harmonic voltage of all the order, and you have to take the square, and you have to take the root mean square, and you have to compare that with the fundamental. Okay, here you should not take the fundamental. So if you take the root mean square of all the harmonic voltage with respect to the fundamental, we can just calculate the total harmonic distortion. So this is total harmonic distortion of voltage. Similarly, if we go for the total harmonic voltage of current, it is nothing but the ratio of root mean square of all the harmonic currents with respect to the fundamental current. Okay. So TDD is the total demand distortion. It is nothing but the ratio of total root mean square of total harmonic currents with respect to the load current. Here we have just taken the ratio with respect to the fundamental current, but here we will be taking the ratio with respect to the load current. Okay, so why we are giving importance to this TDD? Standard 519, IEEE standard 519 gives more importance to this TDD only. It will not consider this THDI. So whenever we go for current harmonics, we have to see this load current, and then we have to compare with that only, not with the fundamental current. But whenever if we are going for the voltage harmonics, we have to compare that with the fundamental voltage. So this THD and TDD, the limits in the IEEE 519 standard will be based on this THD and TDD only. So this has to be noted very carefully. So just you can have a pictorial representation of THDI and TDD. So this green one is a TDD, and this THDI is the red one. So you can see that the THDI will be generally greater, it will be higher, whereas the TDD will be lower sometimes. So always we have to refer the TDD only. That will give you the actual scenario of the system. So based on the load, the harmonics will vary. So we have to look after this TDD only. So do you know what are all the types of power factor? So far we would have seen only what is displacement power factor or a fundamental power factor. So which is nothing but the cosine of the angle between your voltage and the current of the load, right? That is cos phi 1 minus phi 2, where phi 1 is the voltage angle between your voltage and current, right? Cosine of the angle between a voltage and current. But there is also a power factor called true power factor. This comes to picture only when you have harmonics in your system. That is, this power factor takes into account the displacement power factor as well as the distortion factor. Actually, this true power factor is nothing but the product of displacement power factor and the distortion power factor, where you know very well that displacement power factor is nothing but the cosine of the angle between a voltage and current, where this distortion power factor is nothing but 1 by root of 1 plus THD square, where this THD is nothing but the total current harmonic distortion. This is what I have explained. What is THD? So you have to consider that, and you have to take a factor and you have to consider it here in your power factor. Then only it will be the actual power factor of your system. So whenever harmonics are present in your system, you have to consider this distortion power factor and you have to calculate the true power factor. So you should not take the displacement power factor. So that will not give you the actual power factor of the system. So what are the standards that deals with harmonics? We have IEC standard 61000 part 47, that is a general guide on harmonics and interharmonics measurement. And we have IEC 61000 part 430. It deals with power quality measurement methods. Actually, there are a lot of IEC and IEEE standards. Just I have mentioned important standards among IEC and IEEE. Regarding IEEE, we have two important standards. One is 519, that is recommended practice and requirements of harmonic control. And another one is 3002 part 8, which deals with recommended practice for conducting harmonic studies and analysis for industrial power systems. Okay. So all these are important standards in IEEE and IEC that deals with harmonics. I have just taken out from IEEE 519 2014. So they have just given the voltage distortion limit for the system. Okay, so voltage distortion limit is based on the point of common coupling, that is the voltage at the point of common coupling. Okay, so if it is a low voltage system, the total harmonic should be maintained within 8. So based on this voltage, you have to maintain the THD of the system. Okay, so the THD limits are given here, and all these things are the individual harmonic limit. So if you take the total harmonic voltages, it is a THD. If you take only one order, either a fifth order or a seventh order, if we compare that with the fundamental, it will give the individual harmonic distortion. So you have to check that also. So similarly, we have three current distortion limits based on the voltage of the PCC. Okay, so based on the voltage of the PCC, we have to look after the table and we have to check the current limits. So once if this limits are not maintained, what happens actually? So we have to take some optimized solution to mitigate that, right? So once if the harmonic the limits of IEEE 519, what we have to do? We have to go for some filters. Either it may be a passive one or active one or hybrid one. So active filters are very costly actually. Next to that, hybrid filters are costly. Next one, passive filters are economical. But the performance will be in this order only. So active filters will be performing very well, but it will be very costly. So I can say what this passive filter means. It will employ some passive devices like reactors and capacitors to reduce the harmonic frequencies. If it is an active harmonic, it will just provide a compensation wave that will actually cancel out your undesired harmonic components. Okay, so that is why the active harmonic filters are costlier. Here, with the help of this diagram, you can just understand betterly. So here you can just see that this is the source of harmonics, and if you employ a passive filter, simply the harmonic current will flow through this filter. Just it will give a bypass for this flow of harmonic current. But once if it is an active filter, if this is a harmonic current, it will just inject a current which will be in phase opposition to this harmonic current, and finally the harmonic component will be cancelled and the source will be free from harmonics. Okay. So, as of this power quality is enough. I mean, this power quality topic was covered. So I hope I have just given a brief introduction about this power quality and power quality issues. So with this introduction, I would like to move on to the role of renewable integration. So now I just wish to hand over the session to Mr. Sargunan. So he will be handling what is the role of renewable integration and how to deal these issues in the Dix Island Power Factory software.
Yeah. Okay, ma'am. Thank you. Thank you so much. I'm just sharing my screen. Yeah. Hope my screen is visible, right?
Yeah, visible.
Yeah. Okay. Thank you. Thank you, ma'am. Fine. I will just go to the Dixon Power Factory and I will explain about some of the power quality issues and other grid complaint studies. But before getting into that, I will just give you a small introduction about the renewable resources. Okay. Fine. So we will just see about, yeah, here you can see the total installed capacity of the wind generation throughout the world. Here you can see for the different countries like China, US, Germany, and India. Okay. So as far as my knowledge, there are about, this wind contributes about 30% of the total wind generation in around the world. Okay. Similarly, this is the, yeah, this is also the total installed capacity and over the years. Here you can see starting from 1981, here you can see up to 2019, over the years, what is the total installed wind capacity. Fine. I just want to go to an interesting website where I hope this is the CEA, Central Electricity Authority. Okay, I'm just going to that. Where you'll be able to see the what is the total installed capacity, what is the daily generation reports. Say, for example, now at present, what is the, for example, yesterday, what is the total generation? You'll be able to see all those data with the help of these websites. There are many such websites. I will just give you just an insight of all these websites now. Okay. So if you go to the report, here you can see I've just changed from Hindi to English. Okay. Here, if you go to the report, in this monthly report, you'll be able to see the total installed capacity. I will just open that. Yeah, let me just download. Fine. So here you can see the total installed capacity. So basically, I hope you might be knowing this. This total India will be classified into different regions. Like here you can see the northern region, western region, southern region, eastern region, and so on. Okay. And what is the total the installed capacity by the state, by the private companies, and by the uh, central government, etc. And here you can see what is the thermal generation, what is the nuclear generation, what is the hydro generation, what is the renewable energy generation, RES. Okay. And here you can see the, the different generation by different regions. And this is the grand total. Okay. So as far as before month, this is as on 30/11/2020. Okay. So as on before month, here you can see the total installed capacity is around 374 gigawatt. Okay, 374 gigawatt. Here you can see it is given in megawatt. All the capacity is given in megawatt. Okay. So around the total installed capacity as of the before month, it is around 374 gigawatt. Okay. Out of which, here you can see this is the renewable energy generation. This is the renewable energy generation. Here you can see the small hydro power. This is your wind power, and this is your bio power, and this is your solar power. Okay. So here you can see the solar power is alone 36 gigawatt. Okay, 36 gigawatt, and similarly the wind is around 38 gigawatt. Okay. So though you can see that solar is almost somewhat less than the wind, but as you compare with the previous year, yes, you can just get these data from the this CA website. You can just compare with previous years. With the previous years, you'll be able to find out one beautiful thing. this solar installation has been increased over the year. It has been drastically increased over the year. Because of the advancement in technology, the solar panels, the cost has been reduced over the years. Because of this reason, here you can see that the total installed capacity has increased, and this will increase over the years. This will further increase. But when compared to the solar, this wind, though it is 38 gigawatt, which is more than the solar, but this will not be increased to a drastic extent because the installed capacity, I mean, the capital cost is quite high when compared to the solar. And even now, few days back, there is a private company which bid it for about a 30 megawatt plant. They bid it for about 2 rupees. They said that they will be able to provide the electricity, 1 unit of electricity for just for about only 2 rupees. So that is the we can produce that solar power with just cheaply. So that is what I'm trying to say. They said they have bidded that they will produce the power of 1 unit of energy for about 2 rupees. I mean, what I'm saying is the selling price to the grid. Fine. So let me come back to my PPT. Yeah. So I hope I will explain this in the CE website. So basically, in the wind turbine can be classified. I mean, it can be installed both in the onshore as offshore. Okay. Onshore in the sense it will be installed on the land. If it is an offshore, it will be installed on the sea areas, near the sea areas. The reason is because, uh, a few decades back, we all know only the onshore wind turbines. We all know only the onshore wind turbines. There is no thing such as offshore wind turbines. But because of the consistent wind speed in the offshore areas, we have tried to install these wind turbines nowadays in the offshore areas also. Because normally here, let me go to the next slide. Here you can see this is the largest wind turbine generator which is available in the market as of now. Here you can see it is almost this is a GE wind turbine. This is a GE wind turbine which is almost 12 megawatt of capacity. Okay, which is almost 12 megawatt of capacity, and this is the offshore wind turbine. This is not the onshore wind turbine. This is the offshore wind turbine. The similar thing, the offshore wind turbine, the largest capacity is around 5 megawatt. It's not more than that. It's only around 5 megawatt. The reason is because, as I said, the wind speed will be quite consistent in the offshore areas when compared to the onshore areas. Say, for example, in the onshore areas, there will be high-rise buildings, trees, etc. So because of this reason, the wind speed will get reduced. But whereas in the offshore areas, we don't have any such constraints in these offshore areas. So because of the reasons, there will be a consistent wind speed. So because of that, here you can see that the capacities, the largest capacity is 12 megawatt, whereas in onshore it is only 5 megawatt. Okay, this is, I'm saying it, the single wind turbine capacity. Okay, this is a single wind turbine capacity which is 12 megawatt, and they are just comparing it with the other height like the Eiffel Tower, etc. Okay, here you can see the Eiffel Tower height is around 324 meter, whereas this wind turbine height is 260 meter. When it comes to wind turbine, here you can see there are these are the different parts in a wind turbine. Okay, here you can see these are the blades. Okay, these are the blades where the generator will be behind this hub. So this is nothing but your this is called as a hub, where there will be a generator here, and in between that there will be a gearbox where in order to match the wind speed to the generator. So basically the wind speed will be quite less. So in order to just increase this wind speed, they'll be just using these gearboxes in order to increase the speed of the wind turbine. Okay, just give me a minute. Yeah. Yes. In order to increase the speed, in order to match the speed near to the generator, we just normally use this gearbox. And similarly, next to that, here will be able to see something called the pitch control and the yaw control separately. Okay, I will come back to that. I will come back to that. Similarly, here you can see the anemometer. Anemometer is nothing but you will be able to see the wind speed. What is the wind speed? Okay, you will be able to calculate what is the wind speed with the help of this anemometer. So from this input, this will be passed on to a controller where with the help of this, the control mechanism will work here in the hub. Similarly, here you can see the wind vane. The wind vane will basically will tell you the wind direction, at what wind direction the wind speed is high. So with the help of this, the hub will rotate. The whole hub will rotate so that we can get the maximum wind generation. Right. So here you can see the yaw control and the pitch control. Okay, this is here will come the pitch system, and here you can see the yaw controls. Okay, I will explain it in detail here. So there is something called the cut-in speed and cut-out speed. So normally, only if there is a minimum speed, say for example, here you can see only if it is 5 meter per second or above, the wind turbine will rotate and it will generate power. Operating this wind turbine below this 5 meter per second is not quite economical, so it will be in out of operation if it is less than this 5 meter per second. Okay. And similarly, there is also something called the cutout speed. Cutout speed. Here you can see if the wind speed is more than 25 meter per second. If it is more than 25 meter per second, it will not be operated. So normally we'll be having a brake here. Here you can see the brake. So with the help of the brake, it will be made stopped so that the whatever the wind speed, the wind turbine will not rotate. Okay, that is the use of this brake. So after about 25 meter per second, basically this wind turbine will not be used to operate because that is not quite economical. Okay, and I mean the other reason is it will, if it rotates fast, it will totally damage the equipments. It will totally damage the equipments. So yes. So that is nothing but a cut-in speed and the cutout speed. And similarly, here you can see the rated speed. It is normally around 14 meter per second. 14 meter per second. Okay, and yes. Similarly, here you can see the pitch control and the yaw control. Okay, the pitch control is nothing but here you can see this wind blades will be able to rotate, can be made to rotate. So that is nothing but the pitch control. So depending on the wind speed and the wind direction, this pitch control can be altered so that we can get the maximum wind generation. Similarly, this is nothing but your yaw control. Okay, as I said, this hub, this nozzle will rotate according to the wind speed, where it is rotating, where it is flowing. Okay, so that is nothing but your yaw control. I hope with the help of this diagram alone, we'll be able to understand what is the pitch and what is the yaw control. And similarly, here you can see the blades. I mean, normally we'll be having such a question, right? Why are we going only for a three blades? Why not a 2 blades, or why not a 5 blades, or why not a 6 blades, and so on? Okay, we can go with with this 2 blades alone, but this 2 blades, when the wind speed is very high, this will totally collapse. I mean, the wind speed will increase so that it will damage these blades and will damage the whole wind turbine. So that's the reason why we are not going with the 2 blades. Whereas when 3 blades, here you can see the efficiency will also increase. If you go with 3 percentage, I mean, if you're going 3 blades, the efficiency will increase to 3%. But if you're going with 4 blades, the efficiency will increase only to 0.5 percentage. Efficiency will increase only to 0.5 percentage. But for accounting this 0.5 percentage, if we go for this 4 blades wind turbine, the capital cost of the wind turbine will increase. The capital cost of the wind turbine will increase. So that is the reason why we are adopting this 3 blades. Similarly, here you can see that there are 4 types of wind turbines. Here you can see type 1 wind turbine, type 2, type 3, and type 4. Okay, so we will discuss this in detail. So the fixed speed wind turbine will normally will be having an induction generator, and that's nothing but your squirrel cage induction generator. Okay, and this squirrel cage induction generator, will normally draw the current from the utility, so that at the time of starting, it will normally act as an induction motor, not as an induction generator. Okay, so after gaining a rated speed, it will act as a generator. So when it draws the power from the utility at the time of starting, okay, it will draw more starting current. I hope we might be also familiar with these concepts. So during the starting, it will be drawing more current. So in order to mitigate that, we'll be employing the sub starter, okay, so that it will maintain the voltage. So normally, when there is a huge current which is drawing, the voltage will drop drastically at the terminals. So in order to maintain the voltage, we'll be having these sub starters in order to maintain the voltage at the terminal. Okay. So after the starting, we don't require the stop starter, right? We don't require. There is no any purpose of the stop starter. So after starting, this bypass switch will close so that this will export power to the grid, the utility. Right? And similarly, here you can see the capacitor bank. Here you can see a capacitor bank here. Yeah, of course, the use of the capacitor bank, as I said, normally if it is a synchronous machine, we'll be having the capability curve where we can produce the reactive power. But here you will be not able to compensate the reactive power. So because of this reason, because it will not produce any such reactive power. So because of this reason, we'll be having installing this fixed capacitor bank, or we'll be having a switchable capacitor bank, or we'll be having a linearly variable capacitor bank in order to maintain the voltage. Okay, and in order to maintain the voltage and supply the reactive power as well. Okay, so this is nothing but a fixed speed wind turbine. So what all I have said will get covered here. So what all the points which I have told will get covered here. Similarly, here you can see something called the stalled regulator. Another concept called the stalled regulator. Yeah, I will go back to the slide. Here you can see, if we go with stall regulated wind turbine, this stall regulated wind turbine, I will tell you what is pitch regulated and stall regulated is. The stall regulated wind turbine, if we go with this, here you can see the wind speed will increase. It will increase to at a particular point, say for example around 16 meters per second, and after that it will reduce. Though even the wind speed increases, the stall regulated wind turbine, the speed will reduce. I mean the wind generation will get reduced. Here you can see in the y-axis nothing but the active power generated. Okay, so the active power generated by the wind turbine will get reduced after a particular speed. So in order to mitigate this only, we use this pitch control turbine. So this pitch control is nothing but we have seen here, no, this pitch control. So this pitch will be, this wind blades will be adjust accordingly so that it will produce the rated power. Here you can see it will the wind power will remain constant if it ranges from 15 to 25 meters per second. If we use this pitch regulated wind turbine, it will maintain this wind speed. I mean, it will maintain the wind generation, with the active power generation. Okay. Will increase your cost, the cost of the capital cost of the wind turbine. So that's the reason why some will still go with the stall regulator. And apart from that, it will also increase your maintenance cost because here you can see there are moving parts, right? If you have this pitch controlled, there will be such moving parts. So the maintenance costs will also increase. But if you go with the stall regulated wind turbine, there will be no such maintenance cost. Similarly, here you can see this is the type 2 wind turbine. This is a type 2 wind turbine. So type 2 wind turbine is almost similar to this type 1 wind turbine, but here we'll be having a variable resistance. Okay, so that the speed we can increase or decrease, so that we can we can also increase the generation. So that is the reason why we are going with this variable speed wind turbine. So apart from that, it was almost all the same. The other things are almost all the same. You can see the soft starter, the bypass switch, and the capacitor bank. And this is the type 3 wind turbine where we'll be employing the, after the power electronic devices, earlier these two wind turbines were is no longer used nowadays. But still we have such wind turbines installed now. But nowadays we are not totally not using this. The generation has been totally stopped. After the advancement of these power electronic devices, okay, we have been employing these power electronic devices in these wind turbines. Okay, So predominantly now we are using this type 3 and the type 4 wind turbine. Okay, I will just tell you what is this type 3 and type 4. So here you can see we'll be employing a power electronic device, okay, which is a back-to-back AC to DC and DC to AC uh, device, okay. So this will be, normally, since this squirrel cage induction generator, there will be, in order to excite this generation, we'll be getting this power from the utility, okay, where it will give some about 25 to 30 percentage. Normally this rating will be around 25 to 30 percentage, the total capacity, because we need only such power in order to excite this squirrel cage, I mean, doubly fed induction generator. Okay, so this reactive power will flow through this, so it will be excited. Okay, and the active power which is produced will get directly produced to the utility. It will get exported to the utility. So here you can see the coupling transformer. Okay, the three-winding transformer, where you can see this power electronic devices employed in order to produce the reactive power to the generator, where the active power will be exported with. Okay. The type 4 wind turbine is almost same, but instead of 25 to 30 percentage of the wind turbine sizing, here will be going with the total sizing of the wind turbine. Okay, here will be going with the total sizing of the wind turbine. Here the total power, whether it is if you are importing or exporting, the all power will get flow through only this line. Okay. So the disadvantage of going with such type 4 wind turbine is that it will increase your capital cost. Otherwise, you can go with this type 3 wind turbine. So that is the reason why both type 3 and type 4 wind turbine is available in the market. Okay. So apart from this, what are the issues which we are facing while integrating? Right? What are the issues which we are facing while grid integration of this renewable generation sources? So yeah, I hope ma'am have explained about the harmonics part. Okay. So I will try to cover up the low voltage ride through studies. What is the LVRT? Here you can see the voltage ride through studies. What is the other harmonic factors, like ma'am explained about the flicker, and I will explain about the harmonics, and I will explain about the flicker as well. Okay. So I will go to the CA guidelines. Okay. So this is nothing but your CA guidelines, okay, Central Electricity Authority. We have even visited this website now. So they have made such regulations, some regulations, while we are integrating our renewable energy resources to the grid. So okay, so we will see what are all the regulations. Right. So if you have a large installed capacity, okay, if your installed capacity is somewhat high, if you are connecting at voltage level of around 33 kV, okay, if you're connecting at around 33 kV, okay, you will be employed to do such studies. What are all these studies? That is nothing but a grid compliance studies. So first you will be studying this ride through studies. We will be calling this the fault ride through studies, whether it is low voltage or high voltage ride through. So we have to mandatorily do this ride through studies, and the other thing is we have to examine the harmonics. What is the harmonics there in the system? And similarly, we will be also doing the flicker, etc. Okay. So we fine. I will explain what is this fault ride through studies. Okay. So here you can see, say for example, if I have a wind farm, okay, if I have a wind farm, normally this wind farm has a short circuit power of very less. It will be normally around 110 to 150 percentage of the rated amps of this wind turbine. But normally, when compared to the other generation, like your steam turbine generator or your gas turbine generator, the short circuit power provided by that will be very high. But this renewable sources, especially the solar or the wind, the short circuit power provided by these resources is very less. Is very less. So that is one of the major disadvantage of going with this renewable energy resources. Okay. So basically, what we'll be seeing is, yeah. So at that time, what we will have to do is, say for example, if there is a fault in my system, what I have to do is I need to supply reactive power to the grid until the fault is created. I need to supply reactive power to the grid until the fault is created. Because as we supply the reactive power, the voltage will be maintained, right? The voltage will be somewhat maintained. So if the voltage is not maintained, there will be a grid collapse. The voltage will ultimately collapse and there will be a grid collapse. Okay. So in order to avoid such things, we normally do such ride-through studies. Okay. Say for example, if there is a fault in my system, okay, if there is a fault in my system, so here you'll be able to see normally the voltage will get dropped, right? At that line, the voltage will get dropped. So here you can see if the voltage dropped to around 0.15 per unit, the voltage drops around 0.15 per unit. Even if it drops around 0.15 per unit, you need to remain connected to the system for about 300 milliseconds. Okay, here you can see the time, this x-axis is in milliseconds. You need to remain connected for about 300 milliseconds and not only remain connected, you need to also supply reactive power in order to maintain the stability of the system. Okay. So basically why this 300 milliseconds? Because it needs, that is the critical clearing time. Okay. Until this time, so within this time, the fault should be cleared. Normally the fault will be cleared. Okay. So this is where we'll be finding out this critical trailing time with the help of the transition stability studies. Okay, we'll be finding out this critical clearing time, and this protection devices will be used in order to, this clear the fault below this 300 milliseconds. Okay, so normally maximum this critical clearing time with a high voltage or EHV size, it will be around 300 milliseconds. So that is the reason why here you can see even the voltage drops to around 0.15 per unit. You need to remain connected for about 300 milliseconds. Okay. And similarly, if it is 0.85 per unit, you need to remain connected for about 3000 milliseconds. Just nothing but 3 seconds, right? So you need to remain connected for about 3 seconds. And not only remain connected, you need to also supply the, as I said, you need to supply the reactive power to the system. Okay. So that is what you will be basically seeing with the help of the Dixon and Power Factory. Okay. So I will just show you that now. Fine. So let me go to the Dixon in here. Okay. So I've taken an example of a wind farm. Okay, I've taken an example of a wind farm. Fine, I will just explain this clearly. Okay, here you can see there are about 6 wind turbines. Okay, there are about 6 wind turbines, each having a capacity of around 2.5 megawatt, which is operating at 0.9 power factor. Okay. So each wind turbine, all these 6 wind turbine has a capacity of 2.5 megawatt, which is operating at 0.9 power factor. Okay, and here I'll be able to see what is the active power generated, what are all the operation limits. Okay. Here you can see this is nothing but a capability curve of the generator. Yes. And here you'll be able to see that this wind turbine will be normally produced around, I hope here it is 690 volts. Yes, here you can see it is 690 volts. Okay, the wind generation is produced at 690 volts, where it is stepped up. Okay, where it is stepped up with the help of an 2.8 MVA transformer. Okay, 2.8 MVA transformer, where it is stepped up to around 20 kV, which is stepped up to 20 kV, and then it is injected to the grid. Yeah, so here you can see all these wind generation is coupled with the help of a cable. Okay, and this getting injected at this substation, 20 kV substation. Okay. So apart from that, here you'll be able to see a capacitor bank. So this capacitor bank is normally, as I said, in order to maintain the power factor, will be normally just employing this capacitor bank in order to maintain the power factor at the point of common coupling. Okay. So here you can see this is where we are connecting the grid at 20 kV. Okay. So with the help of this cable, which is 0.2 meter cable, which is further extended, and it is connecting at this 20 kV substation. Okay. So what I'm going to do now is basically I'm going to create a fault, so that I will be basically my system will be seeing a low voltage, right? So up in that region, whether I'm going to see whether my wind turbine, whether it is capable of producing such reactive power at such critical conditions. Okay, as I said, the LVRT study. We are basically going to do this LVRT study. Okay. So for that, what I have done is, here you can see this is nothing but your substation. How am I saying that? I will just, here you can see, I will just right click. I will just mark another diagram. Okay, I will give okay. Fine, here you can see. So this is nothing but a substation. Here you can see there will be an isolator. There is a circuit breaker, and the other again there is an accelerator. Okay, and here you can see there is a CT here. There is a relay here, which is feeding the signal to the circuit breaker. So if there is a fault in the system, so it will be sensing that, it will be passing on the signal to the relay, and it goes to the circuit breaker, and it will be breaking that. So even this time, it takes around 200 milliseconds or 100 milliseconds. This operations, the whole things. Okay. So yeah, so basically what I'm doing is, here you can see I'm just making this event. I'm just making an event here. Here you can see I've already created all these things. Okay, I'm just going here. Here you can see at 0 second, at 0 seconds. Okay, I'm just giving I'm just making a fault. Okay, you can see the three-phase short circuit current. I'm just making a fault. Okay, I'm just giving an impedance as well. I'm just giving an impedance here. Okay, so normally I'm just what I'm giving is in an arc fault. So normally if it's a voltage fault, it will be zero impedance. Now I'm giving an arc fault. Okay, I'm just clearing that. Okay, after 0 seconds, I'm just clearing that around 0.5 seconds. Around 0.5 seconds. Okay. So in between this time, I'm going to see whether my my wind turbine is capable of producing such reactive power. I'm going to examine whether my wind turbine is going to produce the reactive power to the system. So to do that, I've just created the fault. Okay, I'm now going to run the initial conditions. Okay, so just going to run the initial conditions. I've just made all these things already. So okay, I'm just going to execute. Okay, and I'm going to run this. Now I'm going to run with the help of for a whole second of 1 second. I'm going to execute. So here you'll be able to see the graphs. Okay, here you can see the graphs. So here you can see this is at the point of common coupling and examining at the point of common coupling. Since we are connecting at this point of common coupling at 20 kV, and I'm examining here. Okay, here you can see, as I told, I've just given a fault with the help of with certain impedance. So the voltage is not fault to zero. It is around 0.3 or something. Okay, it is an arc fault. Okay. So here you can see I've maintaining the fault up to 0.5 seconds, and after the 0.5 second, the fault is clear. The system is, that part is isolated from the system. Okay. So yeah, now we can see at that point, now we can see that my wind turbine is producing the reactive current to the system. Okay, here you can see when the fault occurs, here you can see at the 0 second, it is producing the reactive current. Okay, and it is producing up to 0.5 seconds. And below you'll be able to see beautifully here. At the fault when it occurs, so before the fault, here you can see the wind is producing active power to the grid, it is exporting to the grid. Okay. After when there is a fault, suddenly when there is a fault, here you can see the active power generation falls near to zero, almost near to zero. And here you can see that the reactive power is getting injected. Okay. Earlier it was drawing, before the fault, it was drawing from the grid. Now you can see it is injecting to the grid. Okay. So this is nothing but your low voltage right through studies. Now I have proved that my wind turbine, especially my inverter, is capable of producing such reactive power at the when there is a disturbance in the system. So we can even examine that at the wind turbine terminal itself. So at the wind turbine terminal also you can see here. Okay, there is a voltage drop. So as suddenly here you can see there is active power is reduced, and here you can see that the reactive power is getting injected. Fine. So this is all about the LVRT studies. Okay, this is all about the LVRT studies. So if I go with this other things, like as I told, as ma'am have explained, we'll also be seeing the harmonic studies as well. So if I go here, fine. Here you can see this IEEE 519. So the CA guidelines according India. So if you are connecting at 33 kV, if you're connecting at 33 kV of a large capacity of wind farm, so wind farm or whether it is solar, any generation. So you need to pass through these guidelines. You need to prove these guidelines. You need to pass through these guidelines. So that is why here you can see this CA guidelines. According to India, they are following this IEEE 519 standard. Okay, IEEE 519 standard. Even such here you can see. I hope if Mama have explained, I will just touch all these concepts here. Yeah. So here you can see at the point of common coupling, even if I'm connecting it, normally we will be connecting at 1 kV to 69 kV. So here you can see if it is I'm connecting at, say for example, at 66 kV, the total harmonic distortion should be 5%. It should not be exceed more than 5%, and this individual harmonic distortion should be less than 3%. It should not be exceed more than 3%. Okay. So this individual harmonics is nothing but for each and every harmonics for first order, I mean the second order, third order, fourth order, and so on. We'll be having this such harmonic distortion. This is the total harmonic distortion. So all these percentage should be less than what is provided in this IEEE 519 standard, because the CA guideline follows this IEEE 519 standard. Similarly, this is the voltage distortion. When you come to the current distortion, here you can see we'll be normally going for this IAC by IL limit. This is so important. As I said, we will be normally seeing this IAC by IL limit. So what is this IAC by IL limit? So this is nothing but, as I said, normally if it is a thermal power plant, or if it is a gas power based power plant, the short circuit power produced by these generation will be quite high, because they will be employing a synchronous machine there, so it will be quite high, no problem. But here you can see this these generation will not be able to provide such high short circuit power. Okay, it will be normally around 110 to 150% of your flow lamps. Okay, so this ISBI limit, normally, so that is the reason why we are seeing this ISBI limit. So we normally say that if this ISBI limit is, if it is greater than 20, if the value is greater than 20, we normally call it as a strong grid. We normally call it as a strong grid. Okay, if this value is lesser than 20, if the value is lesser than 20, or in particular, if the value is less than 5, if the value is less than 5, it is called as a weak grid. Even in the CA guidelines, they would have explained if this ISBI limit, if the value is less than 5, you will not be allowed to connect to the grid. I don't know where it is. I will just search for it. Yes, here you can see. Short circuit ratio at the interconnection point where the generating source is proposed, it should not be less than 5. The short circuit ratio is nothing but the IAC by L limit, the short circuit current divided by your load current at the point of common coupling. Okay, so this value should be above 20, or it should be minimum above 5 if you're going to connect to the utility. If this value is less than 5, you're not allowed to connect to the utility. Okay, that is the constraint. Fine. Yes. So this IAC by L limit. So here you can see if this value is less than 20, this is nothing but an individual harmonic distortion. This is nothing but your if it is ranging from 3 to 11th order, this percentage should be less than 4%. If this ranging from 11 to 17th order, this should be less than 2%. If it's ranging from 17 to 23 order, it should be less than 1.5%. So on. Okay. So if it is more than 20, or if it is equal to 20, or if more than 20 to 50, we should follow these guidelines. I mean, when I'm simulating that, this distortion should be less than these limits. If it is more than these limits, we have to provide such like filters or something in order to mitigate this. Okay, so I will just show you with the help of this here. Okay, I will just show you here. So if I go to this wind turbine, okay, if I go to the power quality and harmonics, so this is where we'll be providing this details. What is the harmonics which is injected to the system? Okay, so if you go to the wind turbine and this power quality and harmonics tab, you will be we can visualize these things. Okay, ranging from here you can see if it is given from 2nd to 40th order. Okay, apart from this, here you'll be able to something called the non-integer harmonics, which is nothing but your interharmonics. Okay, so normally nowadays the wind turbine is also injecting some interharmonics as well. So this is nothing but an interharmonics. Okay, fine. So yeah, so what I will do is let me just Yeah, I will go to this project overview, go to the harmonics part. Fine, I will just execute it. So here, if you click this, here you'll be able to see the power quality and harmonics, and the options will get appeared here. So if I just enable here, okay, I'll be executing. I'm just executing it. Fine. Here you can see what is the individual harmonic distortion, what is the total harmonic distortion at this point of common coupling. Okay, since now you can see I'm connecting at 20 kV, right? So we'll see what is it. So at 20 kV, so whatever you see here at this bus is nothing but a voltage harmonics. Okay, similarly, whatever you see here at this branch is nothing but your current harmonics. Okay, so let me go to this voltage harmonics. Here you can see this total harmonic distortion is 0.71, right? It is 0.71. And here you can see if you are connecting at 1 kV to 20 kV, 16 kV. Since we are connecting at 20 kV, I'm seeing here. So here you can see it should be less than 5%, which is very well less than the limit. Here you can see it is only 0.7%. So this is valid. This is okay. Similarly, here you can see the individual harmonic distortion should be less than 3%. Here you can see it is only 0.34%. So this is also okay. And similarly, you have to see for the current harmonic distortion as well. So here you can see for the individual harmonics. And instead of giving total harmonic distortion, here we'll be giving the total demand distortion. So normally you'll be finding out this total harmonic distortion with the help of this, summing up all these individual harmonics, and you'll be taking the square root of that, and we'll be dividing it with the fundamental frequency, I mean fundamental harmonics. So if you divide with the help of this load current, you will be able to find out instead of dividing it with the fundamental current. If you divide it with the load current, you will be able to find out what is the total demand distortion at this point. Okay, so that is nothing but the total demand distortion. So the total demand distortion, if you are connecting, I mean, if the IAC by IL limit, so we can find out what is the short circuit power which is produced, and we can find out what is the load demand here, and if with the help of that we can find out what is the harmonics, individual harmonics, what is the total harmonics. No. So this is all about this harmonics part. Apart from that, here you can see there will be also see the flicker as well. The flicker as well. Even if I will just type it here. Sorry, the spelling is wrong. Flicker. Fine. Here you can see. So in addition to harmonics, the other power quality measurements like the voltage sag as well, the flicker, the disruptions, all these should be maintained according to this IEC standard. This IEC standard, which speaks about this power quality issues, is nothing but IEC 61000. Okay, IEC 61000, where you'll be seeing this power quality issues. They'll be giving such values, what all to be maintained, the things in a given form or in a given system. So they'll be giving in IEC 61000. Okay, so I will just go to a website. Okay, I'll just go to a website so that I can show you this. Yes. So as I said, this is nothing but a flicker. So mainly we'll be seeing this flicker apart from the power quality, other power quality issues like sag and swell. So this flicker, this flicker, the standard is like something like this. This is your IEEE standard, and this is your IEC standard. As I told, no, this is 61000, and this is your IEEE standard 1453. So in India, we follow according to CA guidelines. They follow this IEC standard. Okay, so for the IEC standard, here you can see, IEC standard comes up with different parts. Like it ranges from 1 to 12. So the different part speaks about the different things. So for example, if the part 3 generally speaks about this measurements, how we are going to measure the things. Similarly, the part 4 will give you what is the things which has to be maintained, or what are the required things has to be maintained in the system. Okay, so that is something about part 4. So if we examine this part 4, you'll be able to find out what is the flicker which has to be maintained. So normally this value ranges depending on the kV, as I showed, no, how similar to this harmonics. The flicker also, depending on the kV ranges, it will be varied. Okay, it will be ranging depending on the kV range. Okay, so normally all these value will be less than 1. Okay, all these value, whether it is here, okay, this flicker, normally this value should be less than 1. Okay, say for example, to be in particular, in the IEEE standard will speak about like this, normally we'll be calculating a long term and short term flicker. Okay, the long term and short term flicker. The short term flicker is nothing but it will be calculated for about a period of, um, for a very short period. Okay, for a very short period. For example, whereas this long term flicker will be calculated for about 2 hours. Okay, the short term flicker will be calculated for about 10 minutes, where this long term flicker will be calculated for around 2 hours. So that is nothing but your short term and the long term flicker. So mainly we'll be examining this short term and the long term flicker. Okay. So if I have already run that, so here you can see what is the short term and the long term flicker at the point of common coupling. Okay. Here you can see the short term and the long term flicker will be given both for the continuous operation as well as the switching operation. So basically, flicker is nothing but whenever there is a sudden large variation in a system. Okay, since we are talking about the wind turbine, I will just give you an example of the wind turbine. Say, for example, if the wind turbine is in a rated speed, which is around 12 meter per second, and if this wind speed suddenly falls to 5 meter per second, it's nothing but a cut in speed, right? If this speed suddenly falls to this 5 meter per second, okay, this there will be a sudden loss in the generation. The generation will get reduced drastically, right? So at such conditions, there will be a large voltage fluctuations. There will be large voltage fluctuations. So that is nothing but your flicker. Okay. So this will be examined both for the switching operation and both for the continuous operation as well. Okay. So what example I have given is for a continuous operation. So it will also happen in the switching operation as well. Normally, when you are, if you are braking and if you're operating in the again, okay, in the at the switching operation also it will happen. Okay, so this will be examined at both the continuous and switching operation. Here you can see that at both the condition, here you can see it is very less, which is around, here you can see it is 0.16 and it is 0.6, 0.06, 0.04, which is always well within the limit. Normally, as I said, this value will, all the values, whether you go for any kV, all the values should be less than 1, less than 1. So here you can see all the values are less than 1, so it is okay, it is well within the limit. Okay, so this is all about the grid compliance studies, the renewable energy integration studies. We'll be normally examining this LVRT studies and similarly the HVRT studies. So HVRT is also the same, similar to the LVRT studies. Okay, here you can see if the voltage goes beyond this 1.3 per unit, what will happen? You need to remain connected to such. So similarly, the same thing. If it ranges from 1.3 to 1.2 per unit, what happens if you uh, the voltage ranges from 1.2 to 1.1 per unit? Okay, so it is all you know similar to LVRT. Is this is nothing but a HVRT studies, but we normally give importance to this LVRT, low voltage right through studies, and in some other areas we'll be calling it as under voltage right through studies. Okay, both means the same. Yeah, I hope it is almost 2:30. Uh, if you have any doubts, you can ask me. Or
Yeah.
Participants, please share your questions. You can unmute and you can ask the questions, or you can put it in the chat box. Participants, you can please ask your questions. You can unmute yourself and you can ask the questions. Ma'am,
Yes, ma'am.
I think there's no questions from the participants. Uh,
Okay.
can we wind up the session, ma'am?
Yeah, sure, ma'am.
So I would like to thank Ms.Amudha ma'am for a lucid presentation on the issues related to power quality. I'll also like to thank Mr. Sadgunan sir for his wonderful session on the role of renewable integrations and its power issues. Okay, thank you, ma'am. Thank you, sir.
Thank you,
Yeah,
ma'am.
thank you, thank you.
The participants, the feedback link has been posted in the session. So kindly fill the feedback form. Tomorrow will be the last day for the FTP, and afternoon session there will be a questionnaire session. Kindly, you'll have to attend that quiz program for you to get your certificate. So kindly attend the last session without fail. Any other queries? You can just clarify it now.